Okay, we have a lot of people here remotely, but that's fine. So. See. Still a couple people making up the test, which is why I haven't posted the grades yet. They are all graded. I just wanna be 100% sure on the curve. They should get up today. Because they're finishing the test off. So the next set of worksheets and homeworks are due on the 30th. But the next thing that's due is the semester project topic. If you look at the schedule, it'll say it's due today. I extended it to the 13th because I forgot to mention it. But the semester project topic, I talked about this at the beginning of the year. At the end of the semester, you're going to have a project. You need to choose a topic for that. Choose a topic on which to do the project. So let me go over to Brightspace and show you where you can do that. So I'll go view as a student. So if you go to content, semester project, you'll see. Did I really screw up and make that October the 14th? Escape. Let me just check that I didn't mess that up, but I'll show you where it is. Oops. Oh no, okay, so I just screwed up on here because I cannot remember numbers properly. It's due the 14th, not the 13th. That was a typo on my part. And that means I made a mistake in the announcement as well. So I'll quickly edit that. Sorry. Just quickly adjust these to the right date. But you can find the semester project in content, semester project. This is the assignment to submit your semester project topic. You just need to submit your topic. Attached to the assignment is a list of possible topics, but also they're right here. So if you go to the example presentation topics, you can see for each chapter, there are a few topics listed that you could choose, but you don't have to choose those. You can make up your own if you want. But the most important thing is to not repeat any claimed topics. So here's a list of all the claimed topics. You can see one of them has already been claimed. So make sure you don't choose one from this list. And if you do, I will reject it and tell you. But that's the semester project topic. Please submit your topic by the 14th. You can please choose a topic that hasn't been claimed, and you're not limited to the list of example topics, but they're there to help you make a choice. You don't have to start from nothing. And most people use the example topics. Nothing wrong with them. Just make sure you haven't picked one that's already been chosen. Yeah. And sign in on the sign-in sheet if you haven't already. So we were talking about the interior of the sun. The sun. So we can really only observe the outside of the sun. We have no way to look deep within. Well, we have one, but it's not great. But we can build theoretical models to explain the stellar structure. Because the nice thing about the sun is that it's basically a big ball of, well, hot plasma. It's also all sort of mixed up and, there's no solids or anything. It's just plasma all the way down. It's hot enough that it's always just plasma. So you can actually just work it out with sort of the formulas for plasma physics. So we can build theoretical models with equations for the stellar structure. We can determine the pressure, temperature, pressure, luminosity, and mass at each point in the sun. And then we can calculate a model from the center of the sun to the surface and compare this with what we actually see on the sun and make corrections to improve these models and repeat the process. So what do we know about the sun? It's composed of a plasma. All the atoms in the interior are ionized. So in some ways, this makes it simple. The fact that it's a plasma makes it more complicated, but the fact that everything is ionized and acting kind of like a plasma means that it's all one, basically all one material, which makes it a little easier to analyze. It behaves much like a hot gas. There's no solid or liquid component. And that makes things a lot easier. The sun has been stable for billions of years, so pressure and gravity have to be balanced, keeping the sun in hydrostatic equilibrium. And we also know the surface contention remains more or less constant, because major changes to the surface temperature under the sun would have killed all life on Earth. So we know it can't have changed that much. So we can put limits on how much the sun's output has changed. And we also know that energy will be transferred both by convection and radiation. We know it's going to happen by radiation because you cannot stop energy transfer by radiation. And we can tell that it's happening by convection by looking at the surface of the sun. And using the information we know about the sun, we can calculate a model where energy is generated at the core. This energy moves outwards, first by radiation, and then primarily by convection, until it reaches the photosphere. We can work this out by sort of looking at the temperature and density. Here, the temperature and density is such that radiation will dominate. It's more, and up here, the temperature and density is such that convection will dominate. And the model of the interior needs to match what we see on the photosphere, what we see on the surface. Additionally, there are things like vibrations of the surface. We can make calculations about what should cause those vibrations, things like that. So we know the sun is in equilibrium. The inward pressure from gravity has to balance the outward pressure being generated by heat. So it has to be in equilibrium, balance. So the pressure outward has to be balancing the gravity inwards. And that pressure is generated by the heat of the sun. So this actually turns out that there's effectively a solar thermostat. There's a process by which the sun balances itself. So if the sun has a slight drop in the temperature in its core, this leads to a large decrease in the rate of fusion. Because fusion is hard and a little bit of temperature drop leads to a big change in your rate. And that will lower the pressure of the core, which will cause the core to shrink, contract, and heat up. Because as the core gets smaller, that gravitational energy is converted into heat, and so it heats up. Basically, it gets squeezed, and when you squeeze a gas, it heats up. And that restores the fusion rate to normal. Now, if there's a slight rise in core temperature, this leads to a large increase in fusion rate, which raises the core pressure, causing the core to expand and cool down, and restoring the fusion rate back to normal. So this So, a declining core temperature causes fusion rate to drop, so the core contracts and heats up. A rising core temperature causes the fusion rate to rise, so the core temperature expands and cools down. And this leads to, it's a self-correcting loop. It's what's called negative feedback, which is better than positive feedback. Positive feedback causes something to get bigger and bigger and bigger and bigger and explode. So this is the solar thermostat. It works a lot like a thermostat.
Stars like our Sun produce energy through hydrogen fusion in their cores. The overall process of hydrogen fusion converts 4 hydrogen nuclei, which are protons, into a helium nucleus with 2 protons and 2 neutrons. The process converts mass into other forms of energy because the mass of the helium produced is slightly less than the mass of the hydrogen fused. In the core of the Sun, for example, each second about 600 million tons of hydrogen fuse to make about 596 million tons of helium. The missing 4 million tons of mass become energy in accord with E equals mc squared. This energy is the source of the Sun's luminosity. The Sun and most other stars shine with remarkable steadiness because the core fusion rate self-regulates through a mechanism we call the solar thermostat, which depends on 2 kinds of balance. The first kind of balance, which we call gravitational equilibrium, is a balance between the inward pull of gravity and the outward push of pressure. These 2 forces are balanced at each point in the Sun, which keeps the Sun stable in size. The second kind of balance, called energy balance, is between the amount of energy released by fusion in the core and the amount radiated into space from the Sun's surface. This balance keeps the total thermal energy of the Sun steady. Without this balance, the interior of the Sun would heat up or cool down. Let's see how the interplay of these 2 kinds of balance acts as a self-regulating thermostat. This dial, shown at its middle position, represents the Sun's core temperature when both balances are working together to keep the temperature steady. Suppose the core temperature dropped for some reason. This would cause the fusion rate to drop because the rate of fusion is very sensitive to temperature. The core would then be slightly out of energy balance because it's making less energy than the Sun is radiating from its surface, and out of gravitational equilibrium because the lower fusion rate would cause a drop in the core pressure. Now consider this question. What will happen to the core as a result of the decrease in pressure? Will it contract and heat, contract and cool, expand and heat, or expand and cool? The answer is A. The decrease in core pressure means that the inward pull of gravity will be temporarily stronger than the outward push of pressure, causing the core to contract and heat up until both gravitational equilibrium and energy balance are restored. A slight rise in the Sun's core temperature would cause an opposite sequence of events. The higher temperature would drive the fusion rate up, which would increase the core pressure and cause the core to expand and cool until both gravitational equilibrium and energy balance were restored. This self-regulating thermostat not only explains why stars like the Sun shine so steadily, but as you'll learn later, it can also be used to understand the changes that stars undergo toward the ends of their lives when they run out of core hydrogen and the thermostat can no longer operate.
Okay. So, in the solar interior, solar density and temperature steadily increase as you go towards the center. This is how they increase. They're highest in the middle and they decrease as you go up. This is density and temperature. So, the surface here is like 6,000 Kelvin. The core is like 15 million Kelvin. And the density gets, you can see the density spikes in the center as well. So the energy from the Sun gets out of the Sun while in the radiation layer, energy is emitted and reabsorbed and sort of random walks its way out of the Sun. It bounces around a lot. So lots of pockets of radiation get emitted, absorbed, and random walk their way out to the convection layer, where the packets of gas are moving more freely and cycle up and down. So energy gradually leaks out of the radiation zone in the form of randomly bouncing photons, like this. So it can take quite a while for a packet of energy to leave the core and make it to the end of the radiation zone. And then after that, it will be carried upwards by convective cells, where hot gas will rise and cool gas will sink. And it's certainly a series of convection cells, where lower down you have some and they warm the convective cells above them and so on, until they reach the surface. So the radiation zone is relatively transparent, so you get more transfer of energy. Radiation can travel further, and you get that random walk, while the cooler convection zone is okay. So how we know there's a radiation zone and a convection zone is what happens to the transparency depending on temperature. So convection, you have hot gas rises and cool gas sinks. You get bright spots on the sun's surface where the hot gas is rising, and cooler, darker areas around them where the cooler gas is sinking. And it looks like this. Here is where hot gas is rising. These darker lines in between are where cooler gas is sinking. And this is convection. You can see the same thing in a hot cup of water, a boiling pot, things like that. And the bright bulbs on the photosphere correspond to where the hot gas reaches the surface. So the visible top layer of the convection zone is granulated, where we can see areas of upwelling material, the lighter areas, surrounded by areas of sinking material, the darker areas. And how do we know what's happening inside the sun? So again, we have our theoretical models, but how do we get some evidence about what's going on inside? Well, one of the things is that the surface vibrates. So this is showing a velocity plot. We can use the Doppler effect to measure the speed of the surface as it vibrates. And this lets us figure out how the vibrations on the surface of the sun work out and get an understanding of what's going on with that. So here's another short video about our sun.
Given that we cannot see beneath the photosphere, you may wonder how scientists can be confident of what's happening inside the sun. This confidence comes from three forms of evidence. The first form of evidence comes from mathematical models of the sun. Using laboratory measurements of nuclear fusion reactions, scientists can predict many observable features of the sun, including its radius, surface temperature, and luminosity. These predictions are in excellent agreement with observations. The models also make predictions about the sun's interior structure. We can test those predictions using observations of how the sun's surface vibrates, which tell us about how sound waves propagate through its interior. Again, the model predictions agree very well with observations. The third form of evidence comes from subatomic particles called neutrinos, which are produced by fusion reactions. Neutrinos rarely interact with other forms of matter, and therefore are predicted to fly directly outward from the sun's core at nearly the speed of light. Scientists have successfully detected these neutrinos, providing direct evidence that fusion really occurs in the sun.
And in fact, regarding those last ones, neutrinos, there are literally thousands or even millions of them passing through you right now. The sun generates a lot, but they barely interact with anything, so detecting them is hard. So there's three ways we can study the inside of the sun. We can make mathematical models that predict the interior structure of the sun and compare that to what we actually see of the sun. We can observe the vibrations of the surface, and by understanding how those waves propagate throughout the sun's structure, that can give us an idea of what's inside the sun, much in the way we use earthquakes to understand the interior structure of the earth. vibrations of the Earth, we can use vibrations of the sun to get some idea about the interior structure of the sun. It's a little different, but that's the general idea. And then lastly, we can observe solar neutrinos, which gives us, in many ways, an insight directly into the core of the sun where they're generated. The thing that's nice about neutrinos is that they don't interact with anything. They barely interact with anything, which means nothing in the sun is stopping them. They'll just leave the sun, barely interact with it. It generates tons of them because every fusion event generating a helium nucleus generates 2 neutrinos. And then it is possible to detect them on Earth. And so if we detect them on Earth, we can get some understanding about it. It's hard. Neutrino detectors are hilarious looking, but so how do we learn about the interior? We talked about mathematical models already. We can look at patterns of vibration on the surface of the sun. So you can see how there's little waves on the surface. You can see here, this is a plot of velocity of the surface. It's darker on one side and lighter on the other because the sun is rotating. But there are vibrations on the surface. And that gives us insight into what the interior structure is like. So here's another thing showing sort of the vibration patterns we see on the surface. The sun pulses. It moves in and out at a very small rate. The variations we see depend on the interior structure of the sun, and we can model those because it's basically a big ball of hot gas. So we understand how vibrations move through a ball of hot gas. And this allows for confirmations of our models of the interior or their modification. And this is a reasonably well understood situation. So these colored patches depict gas moving down or up on the surface. And they're sort of bouncing patterns inside. And we can get an idea about the interior structure by how those patterns form because they're going to be affected by the interior structure. It's complex and tricky, but it is possible. Another thing is that whenever you turn 4 protons into a helium nucleus, you get a couple of neutrinos. And that happens all the time in the core. So, we're converting millions of tons of hydrogen into helium. We're making a lot of helium nuclei. And so the core is pumping out lots of neutrinos, solar neutrinos. Now, observations of these neutrinos can give us information about what's happening in the core. So this can give us insight to what's happening in the core. The problem is, the nice thing about neutrinos is they don't interact with the sun, which makes it easy, which means they come out of the sun very easily. The problem is they don't interact with stuff on Earth either. They barely interact with Earth itself. So solar neutrinos are predicted to be formed in the first step of the proton-proton chain when you turn 2 protons into a deuterium. That generates neutrinos. Now, neutrinos are weakly interacting. This is both that they interact very weakly with other stuff in the universe, and also actually they are weakly interacting in a technical sense because neutrinos actually only interact or primarily interact only through the weak force, the weak nuclear force. So they don't interact particularly through gravity or the electromagnetic force like ordinary matter. They do interact, to have gravity, but they have barely any mass. So they have minimal effects through gravity. And they don't interact with the electromagnetic force. That's the important thing, or the strong nuclear force. And so they can travel through the entire sun without interacting. And on rare occasions, 1 in a billion neutrino will interact with a chlorine atom. That's at least our traditional method of detecting them is through interactions with chlorine. This will convert it to a radioactive argon nucleus, which gives off light that can be detected, and this gives us a direct look into the interior of the sun. There are also, you can also get some interactions with like water or ice as they pass through. You can actually get what's effectively like a little shock wave as it passes through, because they travel very fast. And those can be detected. So neutrino detectors, because these interactions are so rare, get ridiculously huge. So neutrinos get emitted directly from the core of the sun and escape to interact with virtually nothing. So being able to observe these neutrinos gives us a direct picture of what's happening in the core. They're no more likely to interact with Earth than interact with Earth-based detectors than they are within the sun. So the way to spot them, you need to have a huge detector volume. So neutrino detectors need to be really big, and they need to not have anything else happening to them. So they need to be really sensitive, able to observe single interaction events, and they need to be really big. Basically, and you really don't want to have any noise. So anything else that could cause events needs to be blocked effectively. So the way you do that is you put them in the bottom of mines and you make them enormous. So here is, this is the one in Canada, I believe. Yeah. So early searches for solar neutrinos. So there was a solar neutrino problem. So here is a detector. You can see this. This is the inside of the detector. This is a huge sphere that they fill with water with chlorine in it. And you can detect the neutrinos being generated. So early searches for solar neutrinos failed to find the predicted number. This was a big deal. They actually only saw about a third of the neutrinos they expected to see. But with this detector, basically they repeated it. So it turned out the reason they only saw about a third of the neutrinos they expected to see was not because the number of neutrinos that they predicted being generated in the sun was wrong. It was not that. It was because neutrinos, our understanding of neutrinos was wrong. So it turns out neutrinos have a small amount of mass. And this means that they can oscillate between 3 different flavors of neutrino. There are 3 different flavors of neutrino. And they can oscillate between the different flavors. And what you can do is that if you do it, and the traditional experiments only detected 1 flavor of neutrino. So, and that's the type that's generated in the sun, but it can change flavor. There's 3 of them. There's electron, muon, and tau. The sun generates electron neutrinos. We detect electron neutrinos. But on the way from the sun to Earth, some of the electron neutrinos can change into muon or tau neutrinos. And what happened was first we detected this happening with artificially generated neutrinos. You generate them in a nuclear reactor. And we had 2 detectors from the same source getting different ratios. So we knew there was something going on. There was actual oscillation. And then we repeated the experiments with the sun with a better designed experiment that could detect all the neutrinos. So like they did the same experiment on neutrinos, one with a way that only detected electron neutrinos and one that detected all neutrinos. And they saw a lot more when they detected all. And so the models of the sun were correct, and we knew that neutrinos had to have mass. More recent observations found the right number of neutrinos, but some have changed form. So On rare occasions, 1 in a billion neutrinos will interact with the chlorine atom and convert to a radioactive argon atom nucleus, which gives off light that can be detected. So basically, neutrino detectors are big tanks of cleaning fluid because that has chlorine. And then they're located in mines well below the surface of the Earth to shield from cosmic rays and other things that could cause false positive events. And the problem was only about a third of the numbers of neutrinos predicted in the models of the solar interior were being detected. And it turned out through a series of experiments, this was able to determine that this was not due to our models of the solar interior being wrong, but it was due to our understanding of the neutrino being off, being incorrect. And in fact, the correct number of neutrinos were being produced, but we were only detecting electron neutrinos and some of them were changing form. So there was some experiments in Japan that first showed that neutrinos could change form. And then there was a experiment that detected all neutrinos. And that found that actually that we were dealing with something. We were detecting all neutrinos and we were not, our models of the sun were correct. So were the solar models wrong? So cooler temperatures might mean fewer neutrinos. And we were having trouble reconciling this. But at the same time, there was actual doubt about the neutrino. Like we didn't know whether or not it had mass because it's got a tiny, tiny mass. So it's very hard to tell. Or did we, were the solar models wrong or did we not understand the neutrino? Because with a tiny amount of mass, the neutrino might be able to oscillate between different flavors. And different flavors would not be detected through the regular method. And actually, in general, people thought it was more likely that the problem was the neutrino than the solar models. Because the solar models were all backed up by all the other evidence. And there was doubt about the neutrino. And it turned out they were right. Now, the problem was the neutrino. They repeated the experiment and was able to show the neutrino had mass. So in 1998, the first evidence of neutrino oscillation was seen. This was in Japan, where they used two different neutrino detectors in the same artificial source of neutrinos, which was a nuclear reactor. That's how you generate, that's one of the ways you generate neutrinos. And then in 2001, the Sun-bearing Neutrino Observatory in Canada found clear evidence of neutrino oscillation. There was what was, if I remember when this came out, it was the salt measurements had come in. Because they did a different experiment where they had salt involved. And so neutrinos can oscillate between three flavors. These are called electron, muon, and tau. They correspond to the three leptons. And during the trip from the sun to the Earth, about 2/3 of the ones produced had changed into another type. And this confirmed the models of the solar interior. And so, let's see if I have more. Here are some neutrino observatories. This is the Sun-bearing detector in Canada. It's a giant sphere in the bottom of a mine, in the bottom of a salt mine. I think this is Super Kamiokande. This is either Kamiokande or Super Kamiokande in Japan. And those are guys in a boat for scale. Those are people. These are all very large, kind of uniquely designed photomultiplier tubes that they use. And a little while back, there was an accident where one of the photomultiplier tubes in the bottom imploded and it caused a wave of destruction and shattered they were filling this tank up with water. And one of the photomultipliers that the fluid broke and imploded. And the pressure wave shattered tubes throughout like the entire filled structure. It was a disaster. There's some fascinating videos about what actually happened there. They fixed it. They just had to replace the tubes and set it up to be more careful. What? Oh, it didn't leak out because the whole thing is sealed. It's also in the bottom of the mine, so. These are inside the sealed sort of water area somewhat. I mean, but these are all vacuum tubes. They're glass vacuum tubes. So they're like this big giant glass fronted tubes. And so when you have mass shattering events, they're not cheap. They're actually the biggest photomultipliers tubes to produce. So, and then since then they still have these observatories going, and we now have observatories that can actually detect where neutrinos are coming from. So the biggest solar neutrino observatory is called IceCube, and that is a cubic kilometer of ice in Antarctica, where they drilled holes down and put in detectors. So they're just using glacial ice as their detector. So learning about the sun's solar interior, this is a full sky neutrino map. Centered on the sun. And this is produced by the Super Kamiokande Neutrino Observatory in Japan, which is this one. So we can now actually figure out the direction neutrinos are coming from their detectors. And the recent big neutrino observatory telescope was IceCube in Antarctica, which is trying to detect neutrinos not from the sun, but from like things way off in space to get ideas from other sources of neutrinos. So models are used to help understand the interior of the sun. Observations can help to refine these models. And the solar neutrino problem is one example. The resolution confirmed the solar model and changed our understanding of the neutrino. So this is the end of chapter 15 and 16. The sun is held together by its own gravity and powered through nuclear fusion. The outer layers of the sun are the photosphere, chromosphere, and corona. The photosphere is the visible surface of the sun. The corona is very hot. The mathematical models and helioseismology give us a picture of the interior of the sun. Sunspots occur in regions of high magnetic fields, while darker spots are cooler. There are darker spots that are cooler. Nuclear fusion converts hydrogen into helium, releasing energy, and solar neutrinos come directly from the solar core. Although observations have told us more about neutrinos than about the sun. And then, so that was 15 and 16. So now that we've talked about the sun, give me a second to open this up. Let's move on to other stars. So let's talk about how we measure and observe the stars. So one of the first things we want to figure out when we look at stars is how far away they are. Because if we want to do anything, if we want to understand how much light they're putting out, we need to know how far away they are. So we can ask ourselves, how far away are these stars? Well, for the nearest stars, we can use what's called parallax. So a parallax is the apparent shift in the position of a nearby object against a background of more distant objects when your point of view changes. So the easiest way to understand what parallax is, or to observe it yourself, is if you close one eye, hold your finger out against the background, some background objects, and then switch what eye you're using, you'll see your finger move. It helps if you get a bigger effect the closer your finger is to your face, and the further away the background is. So the same thing happens with stars and the Earth. We move from one side of the sun to the other every 6 months because we're orbiting around the sun. We move a distance of 2 AU. So a nearby star will move against the background of more distant stars. So that's parallax. So a nearby star will appear to shift against the background of more distant stars. Now, one of the things that happened is early in the history of, back in the 1600s, so 1500s, 1600s, when people were arguing in favor of heliocentrism, one of the big arguments against it was we couldn't see parallax. And that is because stars are so far away that the parallax is tiny. So, the stars we see, the closest star to us is far enough away that its parallax is less than 1 arcsecond of the sky. So if we look at the sky, the whole sphere is 360 degrees. 1/60th of a degree is an arc minute. 1/60th of an arc minute is an arc second. So that is a tiny distance. So yeah. The position of nearby stars is proceeding to shift by small amounts relative to stars as the Earth moves around the sun, and the size of the shift tells us the distance to the star. So like if you're doing that, if you do parallax, one eye and then switch to the other, with your finger closer to your eyes, you'll get a bigger effect than with your finger further than your eyes. And you can actually use the size of the parallax to measure how far away the object is. And it turns out we have a unit to make the formula easy. So you can do a bunch of trigonometry to work it out. But because the angle is so small, it turns out a lot of stuff simplifies. And you can literally reduce it to distance in parsecs is equal to 1 over parallax in arcseconds. Because the angles are so small, you can approximate like trig functions with straight lines. So it turns out there's a simple formula, and this is why you'll often hear about parsecs when people are talking about distances for stars, because that is a unit of distance that's based off of something we can measure directly. Parsec is a sort of abbreviation of parallax of 1 arcsecond. Par for parallax, sec for arcsecond. Parsec. So if something is 1 parsec away, its parallax will be exactly 1 arcsecond. If it's further than a parsec away, it will be less. If it's closer, it will be more. The nearest star to us is more than 1 parsec away. And so knowing this baseline allows us to calculate the distance. So if you take the parallax angle, the distance is parsecs is 1 over the parallax angle in arcseconds. If you want it in light years, well, 1 parsec is 3.26 light years. So you can just take the distance in parsecs and multiply by 3.26 to get the distance in light years. The nearest sun to the star, Proxima Centauri, which is a member of the 3-star Alpha Centauri complex. You can measure its parallax. it's less than 1 arc second. So if you wanted to make a model of the neighborhood, the sun is a marble, the earth is a grain of sand orbiting a meter away. The nearest star is another marble around 270 kilometers away. And the solar system extends about 50 meters from the sun, and the rest of the distance from the nearest star is basically empty. So stars are a long way apart. So these are the 30 closest stars to the sun. Each of these circle, this is 1 parsec of distance, this is 2, this is 3. So there's Alpha Centauri, it's down a bit, that's the closest star, it's a bit more than a parsec away. And these are just various nearby stars. Sirius is the brightest star in the sky because it is both close and a very bright star. So the other thing we can talk about is something called proper motion. And that is like how much the star is moving across the sky, independent of parallax. So the star with the biggest proper motion of any star, so this is the actual shift of the star in the sky after correcting for parallax. Basically, you can just wait a year and measure again and see how far it's moved. So this is Bernard's star. These two pictures, here and here, where you can see it's moved ever so slightly, were taken 22 years apart. And that's Bernard's star. It has the biggest proper motion of any star we can see. And this shows the actual, oh wait, these are the Alpha Centauri. So Bernard's star on top. Yeah, these were taken 22 years apart, showing that biggest motion. And B here on the bottom shows the actual motion of the Alpha Centauri complex. So we see the proper motion, the transverse motion, is about 24 kilometers per second. It's also moving towards us at about 20 kilometers per second. So the total true space motion is about 31 kilometers per second. So you can combine the proper motion of the star with its radial motion to figure out its actual motion. So let's talk about how we classify stars by their brightness and their color. So when we talk about the brightness of a star, we can talk about two things. We can talk about how much light a star is actually putting out, how bright the star is on its own, and we can also talk about how bright we see the star. And those are two different things. So luminosity is the absolute brightness. It's the amount of energy being emitted at all wavelengths by a star every second. And the units we use, the standard unit we use, because no one wants to deal with like the 10 to the 30 watts or whatever it is. We just compare it to the sun. So the standard unit is the luminosity of the sun. Now, apparent brightness is how bright a star appears from Earth. This depends on the distance. So is a star that we see as faint, is it intrinsically faint? Is it actually a dim star? Or is it a bright star very far away? That's sort of the question you have to ask. And so we have various methods that we can use to determine the distance. So how do we measure stellar luminosity? Well, as light travels outwards, it spreads out in a sphere. Because you have the light is going out from all directions from the star, and it's spreading out. So at 1 AU, 1 unit of area gets so much light. At 2 AU, that light is spread out over 4 units of area, and at 3 AU, it's spread over 9 units of area. Which means, if you know how bright you see a star, is, so if you know how bright a star is, how bright you observe a star is, and how far away it is, you can figure out its luminosity. And the other way around is also true. If you somehow know exactly how bright a star is, like you know what its brightness should be, or exactly what it should be, via whatever method, it might be that it's an object that you understand exactly how bright it should be. You can use that to measure distance. So the way we measure distance is sort of a weird mix. So brightness of a star depends on both distance and luminosity. So if you know the luminosity, the brightness we observe. If you know distance, you can figure out luminosity. If you know luminosity, you can figure out distance. So luminosity is the amount of power that the star radiates. It's in energy per second. The standard units would be watt. The SI units would be watts, but it generates so many watts of energy that we just do it in units of the luminosity of the sun. And apparent brightness is the amount of starlight that reaches Earth, the energy per second per square meter. And the luminosity passing through each sphere here is the same. And the area of the sphere is 4 pi times the radius squared. So if you divide the luminosity by the area, you get the brightness. So if you double the distance, you quarter the brightness, because you're dividing by the distance squared. So the relationship is brightness is equal to luminosity over 4 pi times distance squared. So we can determine a star's luminosity if we can measure its distance and apparent brightness. So luminosity is 4 pi times distance squared times brightness. So two stars that appear equally bright might be a closer, dimmer star and a fainter, brighter one. And most of the stars we see at night are actually both bright and close. That's how we can see them so easily. So, how do we measure the brightness of stars that we can see? Well, the system is called stellar magnitudes. So these were developed by Hipparchus in 150 BC. Basically, he was making a survey of the stars in the sky, and he grouped them based on how bright they looked. And he was just putting them in groups and ranking them. So the brightest stars were in the first magnitude, the next brightest were in the second, and so on, down to the dimmest stars, which were that he could see, which were in the sixth. So he grouped stars into categories based on their brightness, where the brightest stars fell into first magnitude and the faintest stars visible were in the sixth magnitude. And this is based on naked eye observations, and it has some unfortunate side effects. It's backwards numerically. A bigger number corresponds to a fainter star. So the faintest object, the faintest objects we can observe with our most advanced telescopes have the largest magnitudes we can observe. It's backwards. It's unfortunate. And it's not linear. A second magnitude star is not twice as faint as a first magnitude star. It's actually it corresponded most closely to a logarithmic scale. So what happened was this system put together by Hipparchus, this grouping he did, was systematized, and actually we put numbers on. So in the 1800s, it was expanded, where each magnitude indicates a factor of 2.5 in brightness. So if you increase by a magnitude of 1, so if you go from magnitude 1 to magnitude 2, your brightness is cut by a factor of 2.5. Specifically, I think the system is that 5 magnitudes correspond to a factor of 100 in brightness. And if you take 2.5 to the 5th power, you will get something very close to 100. And so what it actually is that, so the system is actually based on the fact that 5 magnitudes correspond to a factor of 100 in brightness. because that goes from 1 to 6. That's where that 5 comes, and that was about what you can see with the naked eye. It's a factor of 100 in brightness. And telescopes expand the scale. So our current limit is with the James Webb Space Telescope is in the mid 30s. I think it's like 33, 34. $34. So James Webb gets all the way out to here, 34. And so the brightest object in the sky is the sun at like -27. The full moon is at -12 or so. Venus is -4-ish. Jupiter and Mars are about -2.5. Sirius is like -1 or 1.5. And yeah, this scale. So, and you can have an apparent magnitude, which is what you see, and then there's an absolute magnitude. An absolute magnitude is the magnitude you would see at a fixed distance, and that distance is 10 parsecs. So if you have the apparent brightness of star 1 over apparent brightness of star 2, that's 100 to the 1/5, that's magnitude 1 minus magnitude 2. Luminosity of star 1 over luminosity of 2 is this formula. You don't need to know these formulas, but they are the actual formulas. So it's about 2.5 per step in magnitude. It's actually the 5th root of 100. So apparent luminosity is measured using the magnitude scale, which is related to our perception. It's a logarithmic scale. A change of 5 in magnitude corresponds to a change of factor of 100 in apparent brightness. So you can go from like the sun at -26.7, because the sun is very bright in our sky, it's the brightest thing. And then our limit for star detection is now at 34 with the James Webb Space Telescope. And some stars, so Venus at its brightest is at -4.4, Sirius is -1.5, Alpha Centauri is 0, Betelgeuse is 0.8, Polaris is 2.5, the naked eye limit is 6, Barnard's star is 9.5. And the most confusing thing about magnitude scale is just that larger magnitudes are dimmer. So a magnitude 34 object is very, 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 very faint. Now, at other wavelengths, we just use measurements of luminosity. This works for radio waves and gamma waves, etc. Sometimes the magnitude scale gets used in ultraviolet and infrared wavelengths, but in general, it's not, because it's honestly not the most convenient system, and it's mostly around for historical reasons, which is why it's stuck with. Now, one of the interesting things is that the color of a star is most closely related to its surface temperature. So hot stars appear blue, cool stars appear red. This is Wien's law. And the color doesn't depend on the distance, but it can be affected by stuff in between you and the star, interstellar dust. So interstellar dust will scatter more blue light than red light, and it will redden the star. And if you've ever seen a dramatic sunset, that's the same effect. That's dust in our atmosphere scattering more blue light than red light and reddening the star, which is our sun in this case. So the color of a star is indicative of its temperature. Red stars are relatively cool, whereas blue stars are hot. So here are some examples. So how do we measure this? Well, we can look at the temperature peak, but we can also look at what lines show up in the absorption spectrum, because different temperatures will ionize different amounts of elements. And so we can measure the absorption spectra, see which lines or which ionization lines appear and their relative strengths, and put them into categories. So this is how we get these spectral types, O, B, A, F, G, K, and M. And the reason the letter order is so random looking is because the original system was based around the strength of one particular line. And that line is not strongest at the highest temperature. It's strongest, well, not quite the middle, but in A. So hot stars, but not the hottest stars or the coldest stars. So because of the way the system was invented, the categories are based on one of the properties that's being measured. But that doesn't necessarily correspond directly to temperature. So every object emits thermal radiation with a spectrum that depends on its temperature. So if something gets hot, it glows. The hotter it is, the shorter wavelengths it emits. Which is why if you've ever seen like a light bulb warm up, or if you underpower an incandescent light bulb, it starts off glowing red. Well, it starts off dark because it's emitting mostly infrared. Then it will glow red and then get more and more white. You know, red, orange, yellow, white kind of color. And if you got it even hotter, it can look bluish. You might also notice if you're buying lights or looking at lights, they'll be rated with a temperature in Kelvin. That's because they're trying to match see the spectrum emitted at that temperature. So hotter objects emit more light per unit area at all frequencies, and hotter objects emit photons with a higher average energy. So those two facts combine to let you determine the temperature of the object. And the apparent color gives a general idea of temperature, but it's not perfect. And it can be affected by things like dust in the way, making the star appear red. So we need better measurements to determine temperature. So we can't just look at the color and say, that's bluish, or that's reddish. So what we do to get a more accurate value, a more precise measurement, is we can use what are called color indices. We can measure the brightness or magnitude for two different filters. So we look at two specific wavelengths. The most common ones are U, B, and V, which are ultraviolet, blue, and green. And the difference in the two magnitudes, B and V, is the color index, and that determines the temperature. Because it turns out that's related to the slope. And the slope, if you know the slope of that curve, because it's always the same shape, it's just bigger and moved, you can determine, excuse me, exactly what the temperature is. And this is actually how those infrared thermometers work. So infrared thermometers measure two infrared wavelengths and determine the temperature that way. Negative or very small values mean a hotter star. Positive values mean a cooler star. So here, V is sort of a yellow-green, and blue is a blue. And you can see at the hotter star, because you're measuring B minus V. So the radiation from stars is black body radiation. The black body curve is symmetric. Observations of two wavelengths give you enough information to determine the temperature. So you measure 2 points. The difference between those 2 points tells you the temperature. The hottest stars are around 50,000 Kelvin. The coolest stars are around 3,000 Kelvin. The sun is on the cooler end, but in the middle still at around 5,800 Kelvin. So we look at the absolute and apparent brightness of stars. The magnitude of stars scale is numerically backwards and nonlinear. The color of a star tells us about its temperature, and we can use the color index to find the exact temperature. Oh, okay. It's negative because it's B minus B, but those are magnitudes, so they're upside down. That's what it is. That's why I was confused. But another way we can measure temperature is through ionization. So it turns out, as you change the temperature, different things will ionize. As temperature goes up, you get more, various elements will ionize, various elements will get more excited. This will change the strength of different lines in the star spectrum. Different things will get very hot enough to will begin absorbing, and different things will different amounts of ionization will occur. So levels of ionization also reveal a star's temperature. And we can we can figure out the level of ionization because an ion will have a different absorption spectrum than the neutral atom. So we can determine the amount of ionization by looking at the absorption size lines in a star's spectrum. And by comparing those absorption lines, we can divide stars into categories of temperature. So as temperature goes up, different spectral lines get stronger. So at low temperature, you see molecules, then neutral metals, then ionized metals, then hydrogen peaks around A here. Then we have neutral helium and then ionized helium in O. So stars are defined by their spectra. They show different spectral lines because they have different temperatures. All stars more or less have the same composition, hydrogen, helium, and etc. That's the metals. And the visible lines depend on the temperatures. Cool stars are not hot enough to excite the hydrogen, so you won't see hydrogen lines. Hot stars will ionize the hydrogen, so you'll also not see hydrogen lines because ionized hydrogen doesn't really absorb anything because it doesn't have any electrons left. And stars at about 10,000 Kelvin are the best at exciting hydrogen. And then the scale was originally looking at the strength of the hydrogen line, which is why A is at the peak of hydrogen. So it was A had the strongest, then B, then so on. And so they put together a scale where in the 1880s, Wilhelmina Fleming classified stars by the strength of the hydrogen line. The strongest lines were class A, the next was class B, and so on. And then in the 1890s, Annie Jump Cannon rearranged these classes to be based on temperature. And this is the basis of the classification we use today, with the hottest stars being O, then B, A, F, G, K, and the coolest stars being N. And I think we'll stop there for today. We'll get back to this next time, but these were the original people who were not. This classification was put together by the women working at Harvard as the calculators at Harvard. And unfortunately, they were not well credited for a long time. So have a nice day. I'll see you next week.
Mr. K.
Regarding the question about turning in homework number 2, yes, you can turn it in with pictures on Brightspace.
Oh, okay, thank you.